Okay. It's 5:20 now. We're in our general discussion session. I received a request to do a quick go through the DPS presentation I had about 29P Schwarzmann-Wachmann 1. So bear with me. I thought about doing a democracy, but then, you know. Yeah, that's what I'm trying to do. Are you seeing this? All right. Okay. I will do this less formal than DPS, so stop me whenever you want, and I can answer a few questions. So this is talk about 29P Schwarzmann-Wachmann 1. The original title was the most interesting comet in the world, but it is actually the most interesting Centaur in the world. Image here is courtesy of Charles Chambaud from his 2015 paper? No, 2017? 2017 paper, sorry, yes. And the picture here is Charles Chambaud. No, I'm kidding, no. So, I'm just kidding. For those who know Charles Chambaud, for those who don't know him, this is not him. This is the Dos Equis guy. Yeah, exactly. Exactly. It could be. Anyway, 29P Schwarzmann-Wachmann 1 in stunning velocity here in the GIF file is an object that has a very, very special orbit. It orbits at just under 6 AU with a very extremely low eccentricity, lower than some of the planetary bodies, and an inclination under smaller than 10 degrees. It is basically in a circular orbit. And the reason a circular orbit is so fascinating is because if you just take the delta T, the difference in temperature and equivalent temperature between perihelion and aphelion, it is less than 8 degrees Kelvin. It's basically an object that, in terms of its orbital input, is bathed in pretty much a continuous, steady input of heat from the sun. We don't know of any other example quite like that in small body realm. Its size, radius is about 30 kilometers. It's the best guesstimate we have right now. Again, thanks to Charles Chambaud's work from the last couple of years. Rotation is a good question. It seems to be a very slow rotator, but is it a 10-day slow rotator, a 50-day slow rotator? It seems to be towards the longer edge, but we don't exactly know what it is in terms of that. Albedo is, again, it's a pretty good question. We kind of assume 4%. There's some sort of measurement that seemed to hint towards 4%, but we don't really see the nucleus. Remember, it's always active. It's always spewing coma. It's mostly obscure. We don't know what the albedo function is of the nucleus, the surface itself. Density, again, unknown. At this point, there's several estimates that it's probably around 1-ish, maybe a bit more, maybe a bit less, 1 grams per cubic centimeter. Sorry, I'm working with CGS. It is nearly always active. Plus, it has a relatively short dramatic outburst. So basically, like a toddler. It is the first Centaur to be discovered. It was numbered 1927 II, or 2. It is the first object to actually fit the definition of a Centaur to ever be discovered. It is a transition object on a transition orbit. And what do I mean by that? It has a Tisserand parameter relative to Jupiter of just under 3, which is it's characterizing the objects that are on the border between Jupiter family comets and Centaurs. And it seems to have the same, and it seems like active Centaurs all kind of aggregate around these values of a Tisserand parameter following Fernandez et al. 2018. Its color is consistent with outer solar system population comet nuclei. And this is what I show here. It's a distribution of B minus R for different small body populations of the outer solar system. And this is sort of a value that Ivanova et al. Found for the colors, again, with the caveat that it's not really the color of the surface, the nucleus itself, probably the color of the dust cloud, dust ejecta. sorry. It has both outburst and quiescent activity, and we can see it, and we can see here an example. It's an image taken by Richard Miles, from an Icarus paper, and we see this. It has a huge, kind of fan-like coma structure. It's really bright, really dramatic. There's some asymmetry here, and on the other hand, here we see a collection of outburst activity throughout the years. This is a long-term collection of data from the Spanish group, and they're basically showing here V, R, and I magnitudes of 29p over a period of I think this is covering in total it's about 4 or 5 years. I'm showing about 2 years here, and they seem to suggest that there's an average of about 7 to 8 outbursts per year, which kind of correspond to maybe a 50-day periodicity in rotation. Might be just a happenstance, but we don't know. There seem to be some outbursts that look kind of like really major outbursts. Some of them seem single or double peaked. Does that mean there are multiple active regions? Does that mean there are multiple jets? Does that mean there's a complex interaction between the jets and the active regions? We don't know. Again, we don't have a good picture of the comet nucleus. So outbursts, quiescent activity, and also characterized by CO activity. This is a really nice collection of data and measurement by Kasper Vierskos. Oh, yes, that one. I don't know if Kasper is still online or not. No idea. But this is showing something that we discussed earlier: the time gap between the dust activity and the gas activity. So in blue here, you can see the production rate of CO in molecules per second, and this is a characterized outburst. Marie and Kasper measured it in the radian submillimeter, and we see here the collection of data points for the dust outburst measured in AF rho, and we can see there's a really strong ramp up here in the CO activity. And after quite some time, this is about 10 or 12 days, there's a ramp up of the dust activity, goes back down, there's another ramp up in the dust activity. It doesn't seem to have a gas outburst connected to it at this time. Of course, in order to actually understand any kind of time constant or temporal behavior for this, we need a much longer temporal baseline for that. And Kasper and Maria and Laura's monitoring campaign with the Great Basin Telescope is completing these data sets. And so we see the quiescent dust level activity is about, yes?
Is the 2.5 10 to 28 molecules per second of CO the baseline, the underlying baseline?
It seems like it. It seems, yeah.
Yeah, it's always
there. Yeah. And so the quiescent CO levels are similar to Hale-Bopp at comparable distances. So even when SW1 is not active, it actually is active as most comets that we would expect. Sorry. The CO activity can also be compared with other objects in its category, and what we see here is a table from the 2017 paper showing heliocentric distance versus the normalized CO production rate. It's a CO production rate basically over the surface area of the nucleus, and what we see here in the blue are the measurements for 29p. The other different colors and ticks are for other Centaur bodies, and this kind of straight black line here is the Hale-Bopp activity function, and we can see that 29p SW1 can definitely be characterized as the most active Centaur. It shows the highest levels of gas activity. It's the most CO active Centaur. It shows the highest levels of CO activity. And it's probably one of the most volatile active objects in the outer solar system in general. It's higher activity than Hale-Bopp. At peak, maybe 10 times enriched than Hale-Bopp, while most other objects are at best a few times depleted than what we've learned from Hale-Bopp. If we look at the interior evolution of something, sort of a cometary nuclei that may have similar attributes to what SW1 has, and this is just sort of a, you can call it a modeling fishing expedition. It's basically just to show one realization of a possible nuclei. It has a rotation of 10 days, so not the 50-day rotation period, but not the 1-day rotation period, pretty long. It has a density of 0.8 grams per cubic centimeter, dust-ice ratio of 1, and CO and CO2 and HCN occluded within amorphous ice. We start with amorphous water ice to see if that can be driving the activity, that can be any appreciable component of the subsurface composition and structure. And so what we see here from about 1,000 years of evolution, corresponding to roughly 50 or 60 revolutions, orbits of SW1, we see this kind of complex structure in terms of the mass fraction of amorphous ice. We're close to the surface, amorphous water ice, close to the surface, crystalline ice is prominent. Most of the amorphous ice has crystallized. And as we go deeper and deeper in, we reach a crystallization front that slowly seeps into the nucleus, transitioning to mostly amorphous ice dominant layers. And we see these kind of frozen gas layers of in between on the cusp between the crystalline ice and the amorphous ice. And this is kind of reminiscent to this sketch from Dina Pralnick's Comets 2 paper, showing what a subsurface layering structure of a comet could be like, filled with porous dust mantle, gas-filled pores, crystallization front, gas-filled pores of amorphous ice layer, and going deeper in, the more pristine composition. But remember, this is only one realization, and we don't have a lot to constrain these bulk thermochemical evolution models of a nuclei right now. Sorry. What we see here is a temperature map over different longitudes as the body rotates, and we want to see what's the effect of changing the rotation period and changing the thermal inertia on the evolution of the diurnal temperature. Again, assuming a 4% albedo, and assuming it is pretty much at perihelion. And so what we see here is a sharp drop in temperature between, when we cross into the sundown, sunset region here, which actually promotes, for the most part, the refreezing and redeposition of ice layers either on the surface or very close to the surface. So at a very, very long rotation period, the red curve here, we actually encounter a kind of dark period during the day, the local day of the nucleus, where a lot of material can be deposited at very, very cold, under very cold conditions, and actually can sort of prime the surface and subsurface layers for re-entry into the sunlight and activity yet again on this periodic diurnal evolution. Obviously, this effect changes as the rotation becomes shorter and shorter, and obviously there's a difference if we take lower thermal inertias or higher thermal inertias. Yeah, this was a plug during DPS for the 29P observing campaign under the Virtanen campaign website. And this was a plug for this workshop. So right now you're here. I know. We're moving at the speed of light. And so for a quick summary, SW1 is a natural experiment and minor orbital effects on icy body processing. However, key parameters are still obscured by its coma. We're pretty much removing a lot of the orbital dependence that dominates a lot of cometary and Centaur objects evolution, and just looking at the object's physical and chemical nature as it evolves. SW1's gas activity, the CO that we can measure, does not correlate with the dust activity. It requires a more complex thermal, mechanical, or dynamical mechanism than we can actually pinpoint right now with our available facilities. Maybe LSST will figure out everything. Yes? The inclination of the orbit? It's 9 degrees? We don't know. We don't know. It's we don't even know rotation. The rotation can be anywhere under 10 days or 50 days.
Yeah, because even if you have a very circular orbit, the pole is very inclined to the orbit, you will have a seasonal effect.
Yes. No, it hasn't really been seen. But what I would say is even in that respect, the first order orbital effect on the thermal evolution is removed. Eccentricity is near zero. The temperature difference, effective temperature difference between perihelion and aphelion is less than 8 degrees Kelvin.
I was thinking more like a scenario where you have a disposal of things in one particular latitude, so there the season actually is important.
Yes. Yes, yes. So the seasonal effects here become much more dominant than any orbital effect. SW1 may be young at its orbit. This may be its closest perihelion orbit ever. I didn't show it. I can show it later. And SW1 may require very slow rotation, a refractory mantle, and low thermal inertia to maintain these elaborate and expensive levels of activity in order to support deposition of cold material to cover larger fractions of the surface to then support activity at all at most times that it has been observed. This was basically it. I have some support extra slides if needed. Yes. Do you want? Oh, I have it. I have both microphones.
From my understanding, they saw that too on 67P, that there was no necessary correlation between the gas jet and the dust activity, so to say. Could anyone confirm that? So it could be just a standard process. I think there was a paper that concluded it could be some sort of avalanche that would like eject dust without necessarily
Do you remember?
yes, but not top of my head. That's your work. There you go. Talk.
For triggering outbursts with an avalanche.
So the just have dust activity that is not associated with gas activity.
So mine still typically would still have at least a little bit of gas. That said, if you think about it, if you have a bunch of material falling off of a cliff, it's jostling around, and it's like producing a big cloud in the bottom, right? Like it's not like we can just think of the dust. I mean, so yeah, there's no air, so it wouldn't behave like a cloud of dust like we would expect on Earth, right? Where you have suspended dust particles that move around. But they wouldn't also necessarily just settle straight to the ground. If you have a mass wasting event, number one, I would expect there to be at least some volatiles exposed. But at the very least, you would expect dust to be jostling other dust around. You basically have this, well, for lack of a better term, a dust gas, where the dust is colliding with it amongst itself and scattering particles out. And yeah, I would expect to see this fan of material coming off.
Yeah, I was just to conclude, I was just saying that they were much closer to the comet, and they could also see this dissociation between the gas and the dust activity.
Right, and so I agree with a few issues to take with that. One is the time lag between these outbursts is huge. One. Two, these are major outbursts. So for the detection for 67P of these dissociated events had to have the spacecraft be there, measuring very low levels of these active periods. And we're talking about massive events here. Now, it could be that SW1 goes through massive, this mass wasting, cliff collapses events all the time, basically. And they're not connected with these major areas of CO activity that just come sublimating off. That could be the case. It seems extraordinary, but we don't really know.
I guess I'm saying maybe there's similar processes at work. That's all.
Yeah.
Different scales, like you said. So
Yeah.
Specifically regarding the events, their outbursts, and Alan, I believe that was Paul's paper, Paul Feldman et al. 2018.
You're talking about 67 feet.
Yes, where there were specific. This was detected with Alice UV instrument, where there were specific outbursts where material was seemingly only with gas or only with dust. Oh, it was Andrew's paper? Okay, Steffel. STEFFL.
Yeah, right.
Was that a paper?
Missing a valve.
Was that the paper talking about just categorizing the observed activity into either gas-rich or dust-rich?
No, it's not a general paper about the activity. That paper is analyzing a number of outbursts seen in the UV, not more generally with other instruments as well.
Right, but it's classifying them as either
Dusty
gas-rich
or gas, exactly.
Okay.
Yeah.
Yeah.
Yeah, and there's going to be a substance paper.
I suppose one thing could also be going at play here is another volatile CO, just because there's lots of it, doesn't have to be running the show all the time. Maybe something we haven't looked at before.
Yeah, which kind of reminds me when Maria's saying,
CO is kind of a crutch because it's easy to
yeah.
To measure it.
right?
Mhm.
Yeah.
Yes.
It doesn't mean it's going to also methane into.
Yeah, although we have pretty strict limits on those. We have pretty strict limits on a lot of those.
So another thing that would put a little crutch in that story is that SW1 is, strictly speaking, not in a region where water ice sublimates massively. 67P is. 67P as a comet nuclei, most of its activity is controlled by water ice, either the actual sublimation or some sort of mechanism to weaken cliffside.
If they're not linked anyway.
It could, but then you need to find the right gas for that right temperature gradient, which would then mean that you need to have a lot of that volatile component. No,
I guess what I'm saying is like maybe the dust is not necessarily linked to. What I'm saying is like you wouldn't need any gas, sort of.
What you need a mechanism to have the gas create such a coma.
Yes, in that case, I'm just talking about the dust outbursts that seem to be dissociated with the gas outbursts. All right, other question, if I may, sorry. So if we were to look for another gas that would create this other outburst, would that mean that there's like pockets, like separated pockets of these different gases that would all of a sudden be exposed?
They're separated thermodynamically unless the mechanism that's causing their sublimation is water ice cages, either clathrates or amorphous ice. If it's not that, then they're thermodynamically separated just because of their volatility.
Gal, has anybody attempted stellar occultations on this target?
Not that I know of. I would like to.
Are you putting a lot of effort in to try and get down on the hard deck, or is it just probing the coma?
Well, wherever it goes, we have the DCT for it, so we're not using it.
Okay, I see. No, I was remembering your diagram about how much effort you put in and how much better you
No,
can
we're
do.
in that middle effort.
Okay. Wow.
I would like to support whoever wants to do an occultation experiment. Well, measurement, sorry, on SW1.
Yeah.
There are a few caveats. I mean, we can't see the nucleus as a point, just obscured in the everlasting coma.
Yeah.
So there's this kind of wiggle room inside the coma to pinpoint the actual nucleus. and there will be effects of the coma itself being part of the coma structure itself being part of the occultation.
Okay, if I can ask one more question, I'm just curious with all this activity, does the orbit require non-gravitational forces to be fit, or is it fit purely with Newtonian mechanics?
As far as I know, it's fit with Newtonian. Yeah,
yeah, well, I would like to know, but I mean, it's crazy. It's always active.
Yeah.
And unless it's symmetrical, it's going to be thrusting, and it's been doing this for a while now. And okay, it's bigger than
it's much bigger. Yeah.
You know, so that's gonna work against us. But I'd be very interested to know.
I think
Jan's going to tell us before we go home.
I mean, yeah, I want to say that even the major outburst is not enough.
And there's no A1 or A2.
There's no A1 or A2.
Wow.
I can't hear.
Yeah.
With the microphone too.
Sorry.
According to Horizons, and I think also in the old catalog of cometary orbits, there is no A1 or A2 needed for the 90 years of astrometry we have on SW1.
Right. So remember, we yes, I said
almost
that
100 years, I guess. So,
I said at the beginning, but we do have almost 100 years of astrometry. Big.
Yeah. I mean, all that activity. Yeah, there hasn't been. I mean, it's so massive that all that activity is not giving it. A not. Yeah. Right. Yeah. Yeah. Although, I mean, other people probably know this better than I do, right? But the astrometry is difficult in SW1 because it's so far and because it's so active, right? So, in terms of physical linear distance, you have a little bit bigger error bar than you would on like some point source NEA, for example.
Well,
right?
this is pretty much
right.
This is what
so you can get astrometry, but how do you know where the nucleus is exactly within the pixels? When if the pixels are half an arc second or whatever.
Right. So this is this is 30.
Yeah, you got plenty of space to jostle around the nucleus, specifically within the central pixel of the head.
Yeah.
And so you got so the 3 sigma error, or the error bar on the astrometry systematically is probably bigger than what you would just normally do if you went through the procedure of doing your astrometry like you would with.
But I think if you just take.
Right. So it's not detectably. It'd be cool for somebody to actually try to constrain the mass by this constraint, right?
You mean like at a lower limit?
Well,
how small it could be?
Well, that's one thing you can do. But if you think about it, if it's capable of being pushed around, and we could do a numerical experiment, we the community, not necessarily people in this room, but you could do that experiment, and if it's capable of being pushed around so that not an unreasonable A1, A2 could have been detected, that's telling us that there's an orbit averaging that's taking place all the time, and it's telling us about the source distribution.
Yeah. So right now, the only thing I did kind of calculate is if we take a major outburst, the equivalent, dust produced by one of these, and this is let's say one of these, that's way smaller of a recoil force to act on the nucleus, assuming a radius of 30 kilometers, assuming a density of 1 grams per cubic centimeters. I haven't done what you suggested. But it doesn't seem like it's needed. It doesn't seem like there's
that provides a constraint. Whether it's meaningful or not, you have to run the experiment. But
yeah,
it says something about the mass. That's for sure.
Yeah, I mean, you have a sunward jet, say, going for 90 years every couple months.
It's a mega hill.
And assume some parameters and see what kind of impulse you get. How is the migration wild?
I mean, just in terms of the dust, in terms of throwing out the dust and getting a recoil force, the major outburst of a 7 mag outburst doesn't do. It's much smaller. I don't remember how many, but X orders of magnitude smaller than what you would need to fling the nucleus.
Is that a good assumption though? Like that it's like a sunward jet. I mean, because just visually it looks like the jet like just spraying around everywhere.
Yeah,
The net, well, that's the net force is 0, it doesn't necessarily mean the also.
Yeah, so, I mean-
Pretty well with the, at least for the CO. I need the mic. Yeah, the CO fits very well with the sunward facing jet. If you look at the detail in the profile, the spectral line profile.
This one?
Yes. Was that in your talk?
That was the backup size because
Okay, yeah.
DPS has 12 minutes.
Do we know if the orbit period is like 12 years?
15.
15.
It's something like
Yeah.
that.
Yeah.
So we've been doing this stuff for several orbits with the millimeter wave.
Yes. What's your question?
My question is, do we know if it's always a sunward facing jet?
Yes.
All the way around the orbit?
Yes, it is. Oh, every time it's been observed, it's a sunward facing jet all around its orbit, even though we've been observing it from more than one orbit. We also see a sunward facing jet for Hale-Bopp CO when it's far out, and CO in Aeschylus,
So-
but not Chiron.
It's not surprising that the subsolar flight might be driving
Yes, yes.
sublimation. But in a case of an object that's in an orbit like this, and you see it all the way around, not a come in, come out, hill bop.
Mhm.
Right.
Nearby fall.
Yes.
It's got really high ability, it's pointing at the sun.
Yeah, so it's always on the
Yeah.
sunward side so far.
Could be all kinds of weird stuff. Yeah.
Well, then you're gonna have to. Future work. It sounds like nobody's done the part.
Oh, I was gonna say something
There's a lot of
else.
stuff.
Oh, yeah, that's awesome. Take it back. Nobody wants this.
So the jet that was mentioned in the pictures that you often see, it looks like a comma feature. This is Maria again. That is not the same thing as the CO sunward facing emission we're talking about.
Yeah.
This very different scale we're talking about, and that is something I guess Charles is going to talk about tomorrow. Yeah, that's a different jet.
So just one last. Oh, sorry, Matthew.
I just was trying to clarify the nomenclature with Maria, and I think you've now clarified for me. So you're talking about the CO observations repeatedly are just the quiescent standard hemispheric, probably, activity, as opposed to what Charles is talking about, which is short-lived outburst activity from a small region.
Yeah.
Okay, just wanted to clarify that.
Okay, so just to close out one little tidbit that I didn't have time to show in DPS is I did it was kind of serendipitous. I just said, okay, I'll just took several thousands of particles, some from the scattered disk distribution, some from classical KBO, including resonant objects. It wasn't intended to be debiased, and I just wanted to see what is kind of a general flux for today's Centaur population that we see today. Can we get something out of it? We did. That's not the point. The point was, out of these several thousand particles, serendipitously, I did not mean to do that. I found two particles that have a very complex history, but after about a million or so years, between 1 million and 1.2 million years, hit SW1's orbit exactly. So A and E are less than 2% from the current orbit values.
How many particles did it take to get those two?
So the initial population particles, remember, it's not.
Did you say you did 1,000?
Several thousand. So it was, I think in total it was like 5,000. Okay. I don't remember the split between the SDOs and the KBOs. But remember, it's not debiased. They go all the way through. I didn't stop and sort of redistribute the initial conditions once they passed the first wave of giant planets. But the interesting thing is you don't have to do much in order to get two SW1s with zero effort. Well, the computer does everything, but basically with zero effort. What does that mean about the actual orbit of SW1 and its history? To do more work, but it's a very special orbit, very special object, but it doesn't seem to be a rare occasion in terms of the dynamics in the outer solar system.
Are there more SW1s?
Yes, there are. There's one small one. It's called Linea Grau. It's several kilometers, and it has similar, not the same, but similar orbital elements to SW1. It's much more inclined, which is kind of introduces a bit of a kink because inclination is hard to change. But it shares similar A and E's as SW1. So, yes, wow. Yeah. Okay. Thank you for. It's 5:50.
56. 57 actually now, just turned 57. 3 minutes.
It's 5:56. We have 4 minutes for a quick discussion. 4 minutes of discussion about anything. Yes, Jan.
Just to follow up, sorry, I'm in my teacher voice. Just to follow up the last comment, Charles is also attempting to look for objects that have similar behavior to that, not exactly the same orbit, but similar behavior at SW1 to see if we can see variations on various timescales of the activity. So this is all comets whose perihelia are like 4, 5, 6 AU. So some Centaurs, some JFCs, because they're interior, because the perihelion is interior to Jupiter, and just to see if it's one of those things where like, well, SW1's weird because it's the one we've been studying, but it turns out maybe a whole bunch of stuff out at 4, 5, 6 AU has this crazy behavior, right? So they're obviously the eccentricity isn't as low as SW1, but anyway, Charles will say more about that.
So either for Gal or Maria, the size estimate of 30 kilometers, is that coming from the production rate of CO and an assumption that the whole hemisphere is active? Oh, okay.
Yeah, that's actually from Charles too. So Charles did a solid reanalysis of a bunch of Spitzer data. And we did the coma fitting procedure on the Spitzer imaging at multiple wavelengths. Yeah, exactly. And it works out great. I mean, the coma fitting sometimes is a little bit, how trustworthy is it, right? But in this case, it seems to work out great. And so we got multiple wavelengths, and they all seem to work pretty well with a single Needham. Yeah, so that's basically where that's from.
So what fraction of the surface is active to explain the CO? You do Cowan and Ahern or
Yeah.
modeling.
I was gonna say probably Maria's. I mean, yeah.
And it's a big object. That's the thing. Think about it as a comet.
That's the other reason why the
Yeah.
Well, but that's the typical active fraction.
Yeah.
On Jupiter family comets with water.
Yeah. Yeah. I would only say that just taking the thought experiment of saying, okay, it's too far for water to control everything and exchanging it for a different volatile doesn't work fully because of the volatility and the fractional abundances and the fact that water ice is present. It's just not as active as it is for Jupiter family comets. So even intrinsically, there's something slightly more complex in the interaction of sublimation fluxes or phase changes in volatile ices. I mean, it's not like in the Kuiper Belt TNOs where water behaves like the rock and methane or nitrogen behaves like water ice. It's not a full enough. It's a transition object. It's a hybrid object. So everything is more complex. All right. And it's 6. Yes. Thank you very much, online participants. Thank you very much, in-person participants. Applaud yourself. Day 1.